Hey, welcome back. In my recent posts, I discussed about stacking up transistors to increase the effective length, which might be imperative in technologies such as FinFETs where you don't have an option to increase the length considerably. But it also has other benefits like improved matching. In this video, we'll look at why stacking up of transistors is different from cascoding and also how we can use stacking up to make it work as an actual cascode and not a device with effectively increased length. Before we move ahead, if you appreciate such content, don't shy away from subscribing to the channel and sharing your thoughts below. Let's get started with this stacked device, comprising of two transistors having aspect ratios of W over L. They are biased with a gate voltage of VB. As they are in series, they are restricted to carry the same bias current as well. The first question is, what is the region of operation under nominal conditions? There are two ways to look at this. One is the plain old mathematical way, and the second, the more intuitive and fun way. Note that if both of the transistors were to be in saturation, then their overdrive voltages would have to be roughly equal, as they are identical and carry the same current. Writing that into an equation, we get VB minus VD minus VT of 1 is equal to VB minus VT of 2, where VT is the threshold voltage. Thus, minus VD equals to VT1 minus VT2, which is positive due to body effect. So this is a contradiction, and this contradiction suggests that our assumption was incorrect. We can observe that M2 has a greater VGS than M1, and thus is more likely to be in the linear region. I leave the mathematics up to you guys to verify that is indeed true. It will actually be insightful to do it yourselves, as this circuit is often used to generate the bias voltage for a cascode. It is also referred to as magic battery. If you guys want, then I can cover it in a future video. Now moving on to the more intuitive physics-based approach of figuring out and also remembering which device operates in the linear region. Physically, this is how the cross-section of a bulk N MOSFET looks like. Now when this is biased with an appropriate gate voltage, the channel is inverted, forming an inversion layer beneath the gate. This inversion region acts like an electric field induced N plus region due to the abundance of electrons, and you see a continuous or a continuum of electrons from all the N plus regions. Now you start increasing the drain voltage. You'll see that the channel will eventually pinch off. It is now trivial to see that the bottom MOSFET is in linear region as its channel hasn't pinched off, but the top one is in saturation. So now that's the primary difference between a cascode and a stacked up composite transistor. What if we want a cascode out of the same transistor configuration? Meaning we want both the transistors to be in saturation, but we still want their gates to be shorted, so that we don't have to generate an additional bias voltage for the gate biasing of a cascode. I asked this question in a poll on my channel. Most of you got it right. Let's look at the answer and the pros and cons of using it. So as we just saw, the lower transistor is prone to be in the linear region as its drain voltage falls below its overdrive voltage, VDSAT. That means that if we want it to be in saturation, then we must either lower its VDSAT or increase its drain voltage. Its drain voltage is VB minus VGS of M1 and thus can be increased by reducing the VGS of M1. So we conclude that if M1 is a device with a lower VT, possibly even a native device, then both the transistors can be in saturation. That answers the question from the poll. But why would we want to do it? I already mentioned one reason, that we don't wish to generate another bias voltage. Additionally, in some designs, having a higher supply voltage, let's say 3 volts, we might have 1.8 volt transistors with better properties like better matching or better GM. The caveat is that the higher voltages might cause reliability issues like breakdown of the junctions. In such scenarios, we can consider cascoding as mentioned to shield the terminal voltages such that they are compliant with the PDK limits. The downside is that such special flavors of transistors such as LVT use an additional mask in the fabrication process, which will increase the cost. Well, just a quick note that when you ensure that the voltages are within the PDK limits, you should check it through a variety of simulations, including powering up and powering down as well. If you guys made it this far, consider liking the video. I'd recommend that you watch this video next, which was an absolute banger. See you in the next one.